Hello everyone, welcome to this lesson. So in this lesson we're going to go through the second method of open methods, which is the secant method. And as I have mentioned in a previous lesson, the secant method is actually the Newton-Raphson method where we actually approximate the derivative. So let's actually see how the technique would change in terms of expressing the XR, and also go through 3 iterations as we have done with the previous 3 methods. So if you remember, the Newton-Raphson was basically you're taking an approximation and taking the derivative at that approximation, and where it intercepts becomes our root. And we have defined the derivative as the rise, which is the f of xi, divided by the run, which is xi minus xr, and we have rewritten this in previous lesson as this. Now what we're going to be doing here is we're going to be approximating the derivative using a backward finite difference. Now a backward finite difference, if you remember, in this case we take a function value at a function value previous to the f of xi at a certain step size. In this case, we're going to use a step size of 0.5. So for instance, if my xi is 1, my xi minus 0.5 will be the function value at 0.5. And then we would basically get the difference between the function value divided by the difference between the run will give us an approximation of that derivative using the backward finite difference. So you're basically taking the function value at that point and the function value 0.5 distance backwards to that point to get an approximation for the derivative. So basically we're going to take this derivative function, we're going to basically substitute it within this equation and rewrite this equation, and now we have xr is equal to xi, f of xi, and you can find here is the backward finite difference. When we basically take this equation, divide it down here, the numerator stays down here, and the denominator you can see is in the numerator. So this is what is called the secant method, which is basically where we're approximating the derivative using a backward finite difference. So let's see if we approximate the derivative using a backward finite difference with a step size of 0.5, how will that change our estimations of the root? So let's go to the first example here. So I'm still going to start with an xi of 1. So my initial guess is 1. So what we're going to be doing here, here's the function value, which is f of xi. And if you remember, this is negative 2. And then we're going to take a function value xi minus h to that, and since the h here is 0.5, is going to be in this case 0.5, so we're going to take the function value here, and then we're going to find what is the slope between these 2 points, and then we're going to take this slope, and where it intercepts the x-axis becomes our xr. Now if you see here, this is negative 2 for f of xi, and negative 2.5 for f of xi minus 1, or f of 0.5. And if we use this equation, as you can see here, also the distance between these 2 points is 0.5 minus 1. And we find that the xr, in fact, is 5. So the slope between these 2 points, so the point that intercepts the x-axis because of the slope between these 2 points becomes 5, as you can see here. And 5 compared to 2, you can say I have 150% error using a backward finite difference with a step size of 0.5. So let's actually see if this is going to get better as we go through 2 additional iterations. So here you're going to find that here we have 5, we have f of xi. From this equation, f of xi has 18, so f of 5 is 18. In this case, f of 4.5 in this case is 13.75. So we have the difference between these 2 function values, and on the numerator the difference between these 2, which is 4.5 minus 5, and this is the function value 18 for 5, and xi here is defined as 5. So if we use this equation, we have an xr of 2.88, which is a much better approximation than what we had previously for a 5, and that reduces it from 150% to 44.1%. So let's go for a final iteration for this lesson. So basically we have 2.88 for our new root. In this case, the xi minus 1 is going to be minus 0.5, so it's going to be 0.38. So we have the difference here, and the function value at 2.88 is 3.41. The function value at 3.38 is 1.28. And then we solve this equation for xr. You can find we got an even better approximation of 2.08 with only a 4% error. Okay, so if we compare this to the Newton-Raphson, where we use the exact derivative, we started with a 50 instead of 150, then we reduce it to a 10 instead of the 44 for the secant, and here we have 0.588, but for the secant we have 4%. So using an approximation of the derivative, and it's not a surprise, does yield slightly more error than using the exact solution for the derivative, which means when we're going to be developing the Python code, it's going to take slightly more applications of the secant method to reach the same accuracy as the Newton-Raphson, as we're going to see in the next lesson. Now, to recap briefly what we have covered in this lesson, we have introduced a version of the Newton-Raphson, but in this case we are approximating the derivative using a backward finite difference, and we just merely substituted this derivative in the equation, and now xr is defined in this equation that we have here, and we have gone through three different iterations defining f of xi minus 1, and basically getting 5, then 2.88, then 2.08 for the roots, reducing the error from 150 to 44.1 to 4%. Now again, in the next lesson, we're going to be creating a secant code to get an approximation with 0.1%, 0.01, and 0.001%, and we're going to also investigate how many applications it's going to take to reach each one of those errors, and also we're going to be comparing it to the Newton-Raphson to see the contrast of what happens when you use a approximation of the derivative if you don't have the derivative readily available. Well, that's it for this lesson, and I will see you in the next lesson.